In this video, we'll take a look at power functions and polynomials. So a general definition of what a power function is a function that can be represented in the form f of x equals some constant k times x to a power p, where k and p are real numbers and k is called the coefficient. So there's some examples of power functions that you've worked with already are the constant function. We have f of x is equal to 1. So you could think of that as being x to the power of 0. F of x equals x to the 0. And then powers of x, x to the power of 1, 2, 3. And then what about f of x equals 1 over x, the reciprocal function? We can rewrite that as x to the power of negative 1, so that's what makes it a power function. 1 over x squared can be written as x to the power of negative 2. The square root function can be written as x to the power of 1/2, and cube root can be written as x to the power of 1/3. So as long as x can be written to a power of a number, it could be 0, it could be positive, could be negative, and it could be a fraction, then those are considered power functions. So what do power functions look like? And we're going to talk about something called end behavior. So end behavior of a function is what happens to the f of x or the y values as x gets infinitely large or infinitely small. We've graphed some of the power functions, even degree, x squared that you've worked with, x to the 4th, x to the 6th. So notice the even degree, the shape is basically the same, except they get flattened out towards the bottom the higher the degree, and they're closer, increase faster, closer to the y-axis the higher the degree. End behavior means as x approaches negative infinity, what happens to the y? So, or the f of x. So as x approaches negative infinity, as x values get smaller and smaller, the y values get larger and larger. So as x approaches negative infinity, f of x approaches infinity. Then also in behavior, what happens as x gets larger? X approaches infinity. So as the x values get larger, on the graph, the y values, or the f of x values, approach infinity. So as x gets smaller or larger, the y values get larger. For odd degree power functions, we've got graphed x to the 3rd, x to the 5th, x to the 7th. They look same basic shape, but notice for the odd, as x approaches negative infinity, as x gets smaller, y also gets smaller. Y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So these power functions were all positive coefficients, but evens or odds. So to sum up in behavior, if you have an even power function and a positive constant k, then your graph is going to be this U shape. As x approaches positive or negative infinity, y approaches infinity. If you have a negative constant, like a negative x squared, negative x to the 4th, then your graph is going to open down. It's a reflection over x-axis. And as x approaches positive or negative infinity, your function is going to approach negative infinity. Then for any odd power, as x approaches negative infinity, y approaches negative infinity. As x approaches positive, y approaches positive. But if the constant up front is negative, such as negative x cubed, negative x to the 5th, your graph again reflects over the x-axis, so it's going to be opposite. As x approaches negative infinity, y gets bigger. As x gets larger, y gets smaller. So this is true for both power functions and polynomials. How to find the end behavior? You determine whether your power is even or odd, and in this case for a polynomial, you find your highest degree, which we'll talk about in a minute, and see if your highest degree is even or odd. And then determine whether the constant is positive or negative. Are you multiplying your even or odd x to the power by a positive number or a negative? And then you can use this figure to identify end behavior. So end behavior is one of the how you tell what a graph looks like when you're taking a look at an equation. A polynomial function adds more terms. So you've worked with polynomials for a lot of polynomials in your math life. So polynomials are things like a linear equation. 2x plus 1 is a polynomial of degree 1. X is to the power of 1. You've worked with quadratics. 3x squared plus x. Quadratics are polynomials. The degree 2, the highest power is 2. So a polynomial has as many terms, could have several terms. 7x to the 6th plus 2x to the 4th minus 1 is a polynomial. Your powers on x have to be positive whole numbers, so or 0. If you think of a constant, that's x to the 0. So polynomial strings together terms where x to the power has to be a positive number. No fractions, no decimals, no negatives. And we usually write polynomials in descending order. That means you write your highest power first and then descending. The first term of your polynomial, the highest power, is called the degree of your polynomial. The number in the front times your power of x is called the leading coefficient, and those two together, the first term, is called the leading term. So in an example, if we want to find the degree, leading coefficient, and constant term of a polynomial, we first make sure we write it in descending order. So this polynomial has the largest degree, 4x to the 6th, so we write that first. 4x to the 6th plus x to the 5th. The next degree would be minus x squared plus 6. So we've got descending order. The degree is the degree of the highest term, 4x to the 6th, so the degree is 6. The leading coefficient is the 4, and it's positive. The constant term is the term that's not multiplied by x. It's the constant 6. You can think of that as 6x to the 0, but the constant in this case is 6, and it's this value right here. So just to practice in behavior, this is 4x to the 6th. It's got even power, and it's multiplied by a positive. So I know that end behavior is as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches infinity. I know that the end behavior, because it's even though it's a polynomial, some stuff could happen in here, but the end behavior will be the same as it is for the power functions. So polynomials have other features because we have all of these extra terms. So we have things called intercepts and turning points. So a turning point of a graph is a point at which the graph changes direction from increasing to decreasing or from decreasing to increasing. The y-intercept is the same definition as we've had. It's the point which the function has an input value of 0. The x-intercepts are the points in which the output value is 0. So y-intercepts are where your graph crosses the y-axis. X-intercepts is where they cross the x-axis. So if we want to find these characteristics, the intercepts, determine the y-intercept by setting x equal to 0. Determine the x-intercepts by solving for the input values that have an output value of 0. So this is the same method whether you've got a quadratic or a polynomial. So given the polynomial function, it's already factored. Determine the y and x-intercepts. So the y-intercept, let x equal 0. So we're going to find f of 0. So we substitute 0 into the function. Don't multiply it out. Use it in factored form. So f of 0, we're going to end up with negative 2 times 1 times negative 4, which is 8. So that tells me that f of 0 is equal to 8. So the coordinate when x is 0, y is 8. Then to find the x-intercepts, set your function x minus 2 times x plus 1 times x minus 4 equal to 0. So you let your function equal 0 and solve for x. It's already factored, so we can set each factor equal to 0. Add 2 to both sides. X equals 2, -1, and 4. So your 3 x-intercepts are the coordinate 2, 0, -1, 0, and 4, 0. Okay, so if you have a function that's not already in factored form, for example, given the function g of t equals 4t to the fourth minus 52t to the third plus 168t squared, factor to find your horizontal intercepts. So here we're talking about g-intercepts and t-intercepts. So to find the g-intercept, let t equal 0. So if I take g of 0, I get 4 times 0 to the fourth minus 52 times 0 cubed plus 168 times 0 squared. I'm going to end up with 0. So the g-intercept is the coordinate 0, 0. Then to find the t-intercepts, take the function itself, the 4t to the fourth minus 52t to the third plus 168t squared, and set the function equal to 0. We don't have any other way to be able to solve this other than factoring at this point. So take a look and see if we can factor anything out. The greatest common factor, I think 4 goes into everything. 52 divided by 4 is 13. 168 divided by 4 is 42. So I'm going to factor out a 4. And then the highest power of t I can factor out is t squared. If I take the greatest common factor out, I'm left with t squared minus 13t plus 42 equal to 0. Now I can solve the resulting quadratic. I have 4t squared, t and t, and if it factors, I'll have two numbers so that when I multiply them together I get 42, and when I add together I get 13. 6 times 7 is 42, 6 plus 7 is 13. In order to have that a negative, I need -6 and a -7. Then set all three factors equal to 0, including this 4t squared that you factored out up front. And when you solve, divide both sides by 4, you'll get t squared equals 0. Square root both sides, you get t equals 0. T is equal to 6, and t is equal to 7. So your t-intercepts as coordinates are 0, 0, 6, 0, and 7, 0. All right, next example is the same type of example. Find the zeros, the horizontal intercepts, and vertical intercept. But I've added in another vocabulary called a zero. So a zero, an intercept is the coordinate. A zero is just the number on the x-axis where it crosses. So when you're finding horizontal intercepts, you'll have zeros at the same time. So we're going to take this equation right here and factor it. And I picked this one because you may or may not have factored using this particular method. So to find, we're going to first of all find the zeros and horizontal intercepts by taking the expression and setting it equal to 0. So we get 2x to the third plus 7x squared minus 10x minus 35 is equal to 0. This is not a quadratic and there is no greatest common factor, so look for a method called grouping. Group together the first two terms, 2x to the third plus 7x squared, and factor out the common factor. X squared is common to both, so I factor out an x squared. I'm left with 2x plus 7. Group together the next two. My goal is to get a factor of 2x plus 7 here as well. Is it possible? Yep, 5 is common to both, and if I take out a -5, I'll be left with 2x plus 7. So factoring by grouping is factor out greatest common factor from the first two terms, the next two terms, and then the goal is to make sure that they have the same factor of 2x plus 7. Now take out the greatest common factor of 2x plus 7. And what you're left with is x squared minus 5. Now I've got it fully factored. Set each factor equal to 0 and solve each. Subtract 7 and divide by 2. We get x equals negative 7 halves. Add 5 to both sides. And then square root. I get plus and minus square root of 5. So the zeros are just a list. Negative 7 halves, square root of 5, negative square root of 5. But the horizontal intercepts are the actual coordinates. Negative 7 halves, 0, square root of 5, 0, and negative square root of 5, 0, and separated by commas. Those are the horizontal intercepts, or the zeros. The vertical intercept is what we get when we take and substitute 0 into the function. That would give me 2 times 0 cubed plus 7 times 0 squared minus 10 times 0 minus 35. So all of these terms end up being 0, and I'm left with negative 35. So the vertical intercept is the coordinate 0, negative 35. All right, so that's a review of basically solving polynomials by factoring. So a general note, a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So notice we had a degree 3 polynomial and we had 3 zeros or 3 horizontal intercepts. Up here we had a degree of 4, and we actually ended up with 3 answers, but this t squared equals 0 occurs twice. So 0 is actually something called a multiplicity of 2. It occurs twice. And then 1, 6, 1, 7. So it actually had 4 answers. It just means that t equals 0 occurred twice. Okay? And then we'll also have at most n minus 1 turning points. So an x cubic looks something like this. This is a turning point, turning point. It has at most 2, 1 less than the degree. So you'll have questions that ask you, without graphing, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points. So for this particular polynomial, it has an even degree, a leading coefficient of negative 3. So if it asks, end behavior does this. As x approaches negative and positive infinity, the function approaches negative infinity. So that's end behavior. Also, since x to the 10th is the highest power, it has maximum of 10 intercepts, horizontal x-intercepts. So a maximum of 10. And then it has at most n minus 1, 10 minus 1, 9 turning points. So we don't know exactly what it looks like, but that's what we can tell just by looking at the equation. All right, so let's take a look at a graph and see what we can figure out, conclude about a polynomial represented by a graph based on its intercepts and turning points. So we can take a look again to review in behavior. Is the leading coefficient positive or negative? Well, in behavior on an odd function goes this direction. Look back at the chart. So that means the leading coefficient has to be negative. Okay. Is the degree even or odd? Well, since it's pointing in opposite directions, the degree is odd. Then the turning points. There are 2 turning points. there are 3 zeros and there are 2 turning points. So the degree, the possible degree, is degree 3. So it has to be odd and degree 3. So just a note about turning points, they're also called local maximum or local minimum points. As your function goes from increasing to decreasing, that's a local maximum. This graph has 2 of them. The local minimum goes from decreasing to increasing. And a global maximum is there is no higher or lower function value on the graph. It's like an absolute maximum. There is no other possible higher y value or function value on the graph. So sometimes we'll call it global, sometimes we'll call it absolute. All right, last example. Determine the zeros and vertical intercept of this polynomial function. And I do not want to multiply it out, okay? So the zeros, since it's already factored, set it equal to 0. The zeros are another word for the x-intercepts. So I have x plus 9 squared, or x plus 9 equals 0. And notice, it actually occurs twice. X plus 9 equals 0, x minus 12 equals 0, and x plus 6 equals 0. When I subtract 9 from both sides, I get the same answer twice. X equals negative 9, x equals 12, and x equals negative 6. So the zeros are a listing of just the x coordinates, negative 9, negative 6, and 12. The horizontal intercepts are the actual coordinates, negative 9, 0, negative 6, 0, and 12, 0. The vertical intercept is what we get when we find f of 0. So if we substitute a 0 in here, I'm going to end up with 0 plus 9 squared times 0 minus 12 times 0 plus 6. So I'll end up with 81 times negative 12 times 6. So let me put that on the calculator. And I end up with negative 5,832. So the vertical intercept is when y is 0, we get negative 5,832. And then just a note, what's the degree of the polynomial without having to multiply it out? Add together the degree of each of the factors. So we have x plus 9 squared, x minus 12 is to the power of 1, x plus 6 is to the power of 1. If you were to multiply that out, please don't. Add 2 plus 1 plus 1, and the degree of the polynomial is going to be 4.